Gibbs energy by melting curve. But it's widely known that there is a lot of errors happens if you use this method. So instead of this, the scientists try to use the electrophoresis method to calculate Gibbs energy as the sum of the Gibbs energies of adjacent motifs. So why it's important to calculate for high accuracy? Firstly, the thermodynamics of DNA is widely, it's really handy in nucleic acid biotechnologies. Those are used in medicine, like diagnostics or therapeutics, and when we try to replicate certain or cut off certain DNA strands in treating disease, or capture certain prompts to detect certain viruses, like in COVID, for instance. And as well as it's on top of this acid biotechnology, it was used in nucleic acid nanotechnology. We know that this is that DNA is now widely used in 3D shapes or in software circuits, constructing machines, and performing as a logical functions. So knowing how in a high accuracy the thermodynamics, how those motifs zip with each other, it's highly needed for nowadays society, community of scientists. Why thermodynamics matters? If we calculate in high accuracy delta G, we can know that our DNA strand is highly possible to occur, and it won't break up easily. And it's here stated that the errors occurs about 1.5 degrees, and it's equals to 3 calorie per mole error energy, and it's pretty high to use those statistics in those above mentioned areas, because it's highly prone to errors. So here I would like to show what the author scientists did differently from other sciences, other articles. So they designed a DNA strand exchange reaction whose total energy equals to the energy of specific DNA motif. As I mentioned, they decided to take overall Gibbs energy as a sum of specific motifs energy. And they measure how much of each DNA molecule exists at equilibrium, and using those concentrations, they calculate the equilibrium constant, and from it, they calculate Gibbs energy. So here they use a catalyst. As I said, catalyst doesn't. They take place. They enter the reaction and accelerate it.
Sorry, please. Daniya, can you add other our group mates? They can't join.
Okay, 1 minute.
Oh, yes.
I think everyone has entered.
Yeah,
now.
okay.
So let's continue. So The scientists use a DNA catalysis because it's otherwise the reaction that they're going to do will take place 100 days, and if this happens, it will be highly prone to errors, which is not what they want to target. So after applying the new method, they used 80 terminal fluorophores to see how fluorescent labels affect DNA stability, 160 single nucleotide dangles, single unpaired base at DNA ends. Those are the tiny red pairs, as you see here. It's called dangles. And 140 multinucleotide dangles, longer tails of unpaired base. very low DNA concentration used, and equilibrium can take weeks or even months to take place naturally. So that even though the reaction design is conceptually sound, it's not practical unless equilibrium can be reached very quickly, as it will give a lot of errors. This issue we'll set it in the next chapters. Yeah, it said here that it will take approximately 100 days to take place here as in the above of the chapter. I think it's but everything to know about it.
Okay, write your name, please. I will ask on the WhatsApp. Okay.
Me or who?
No, the student who wants to ask questions, ask the question, and don't forget to write your name on the WhatsApp. Go ahead with your question.
And traditional thermodynamics that come from the Meltkov experiment, as I said, and experiments in that are done in highly salty buffers. For instance, they used 1 molar sodium buffers and at high temperatures, which don't reflect psychological conditions, physiological conditions. And this creates errors in delta G predictions and of roughly 3 calories. And the new native catalysis method, instead of measuring delta G directly on the native buffer and temperature, eliminating those biases and giving true free energies relevant to biological and nanotechnological systems.
Okay, thank you, Thagi. Another student who wants to ask questions. Remember that we are evaluating the participation of the students. Okay, the next students, please prepare your slides, okay? In slides, it's just not give the paper here and speak about the paper. No, I told you before to present your slides, okay? And also record that. So suppose that you are recording in whatever, using whatever program, not needed the Google Meet, in whatever program, and then the video link to send us. Go ahead, question.
Yeah, I have a question. The article says that the innovation that enables this approach is DNA catalysis system, and has like accelerates forward and reverse rate constants by order of magnitude. And can you explain how this catalyst works and why it's important?
The catalyst is designed to DNA strand that temporarily binds to the reactants, forming an intermediate that allows rapid strand exchange. It doesn't affect the equilibrium position itself. it just accelerates both forward and reverse reactions, and it allowing the system to reach equilibrium within minutes, as without it, it will take 100 years or 100 days. This is critical because without it, some DNA reactions will take a lot to produce byproduct, and this period is so long it will create unnecessary errors and make accurate delta G measurements inaccurate.
Okay, thank you.
Thank you. Okay, go ahead.
So I have the question that's in the article says that after reports that multinuclear dangles destabilize nearly to the DNA, asymptoting at 0.56 kilocolmol, so above at single nucleated dangle for dangles or longer. So what does this results tell us about the physical behaviors of DNA ends?
It shows that when several unpaired nucleotides extend from a DNA duplex, they cause slight destabilization, but probably because of electrostatic repulsion and reduced base stacking. However, this effect levels off after about 8 nucleotides, meaning that longer trails don't continue to weaken the duplex further. This is a new quantitative finding and unavailable from older melt curve data due to their noise and inaccuracy.
Thank you.
Write your name, please.
My name?
Write in WhatsApp.
Okay.
Any other question? Okay, if there is no question, don't forget, please. Yeah, thank you. Don't forget, please, to present the next student to present the slides. Okay, PowerPoint is not just put your, it's not just show you the paper or the article and just speak. No, I told you before to prepare PPT slides and discuss about that. Okay,